Hello there. In this section, we're going to look at how to use tables and technology to do some integrals. So it's really an extension of everything we've done so far in Chapter 7. And let's get started. All right, in this section, we describe how to use tables in mathematical software to integrate functions that have elementary antiderivatives. And what we talked about in the last section was that there are some integrals that just can't be done. In fact, there's a lot of them. So no matter, if you're trying to do just some integral in the real world and you get some strange function as an answer, and it's not an elementary function, that's the stuff we're going to cover later in the class. So in the back of your book or ebook, there's a list of integral formulas. I have them right here. So I have the book and the ebook, but they just look like this, right? Just table of integrals. There's a whole bunch of them. They're in the ebook too. They're easy to find, right? They're called formula cards, just on your table of contents, or to the index. Either way, it doesn't matter. Just scroll down and you'll see formula cards, and we're using pages 6 through 10 to look up the formulas. So it's just the integral formulas. There's over 100 of them. When you're doing the homework, you're going to click a link that'll open up the formula chart. It's up to you how you want to do that. I highly recommend you shift click those links on a Windows computer, or it will close your window and you'll have to go back in and restart. So it's best to have that the list of integrals already open in a separate window. That way you don't have to keep flipping back and forth in the same window. All right, so integral formula number 24. Let's see, it's right here. I don't know if you can see it, but again, you can look it up on your ebook as well. Number 24 is right there. That's what we're going to use. That big happy thing. All right, and we're going to use that formula to do this integral here. So according to the formula, we need a squared plus x squared over x squared. Or it might say a squared plus u squared over u squared. We really don't have that, right? We have to get it in this form, a squared plus u squared over u squared. So just like move everything around until it looks the way you want it to look. So I noticed that the denominator u squared, I have x squared. Remember, u stands for a function, a stands for a constant in the formulas. So 9 is going to have to be a squared. So that means 16x squared has to be u squared. So you got some options here. You can either factor out the 16, or this is a little easier on the algebra, just multiply by 16 over 16, and then switch the order in the numerator. That gives me what I want here. So whatever this is here, I want it to appear down here. So this is like the algebra-friendly way to do this. Now I have what I want, right? So a squared is 9, so a is 3. U squared is 16x squared, right? So all I did is just broke everything down so I could do the substitution. When you plug into the formula for the answer sheet, you want to have everything broken down as u equals this thing, a equals this thing. Don't try to just move it over mentally because it gets too confusing. Just write everything down. So we have what we want, right? U is 4x, a is 3. And then there's what the formula is going to look like. So we're going to plug everything in. Right? So we're going to plug in u. Wherever we see u, we're going to plug in 4x. Wherever we see du, we're going to plug in a quarter. A quarter. It's 4dx. So when we see dx, we're going to plug in a quarter du, and a equals 3. So what that does, it means we can't use this formula the way it appears immediately, because we don't have du, we have a quarter du. So in the next step, instead of mixing x's and u's, I just plug in 1/4 du, and this 16 has to go over here. So the formula that I put at the bottom is exactly the way it appears in the formula sheet. But you have to be able to fiddle it around. du might not be du. It might be a quarter du. And there might be a constant out front, right? So I plugged in a. A never changes. But I didn't want to mix x's and u's. That 1/4 and that 16 cancel down to a 4. And then I plug in the rest of the formula. Then I replace u's with x's, with its equivalent, the 4 x's. And then I just take one more step to simplify, and I'm done. So notice we didn't actually do any calculus here. We did problems like this earlier, like on the first exam, you had some problems like this, where you had to derive certain formulas and things like that. But this is the same sort of thing. Like, this is, if I just gave you the formula and said, prove this formula, that's something you should be able to do. You would use this technique. You would use trig substitution, and it would work out. So this just saves us a little bit of time. So that's how you use the formulas. So let's do another one with a different sort of formula. Now we're going to use integral formula number 73. Let me find it in here. All right, number 73 is right there. Sine to the n du, and it's this big thing. So we saw formulas like that back in section 7.2, and we proved the reduction formula for cosine. I'm sorry, for sine. So let's use it. Let's do sine. So this is, like I said, a straightforward application of the power reduction formula. So here's what the formula looks like directly. N is clearly 6. This is a definite integral. When we did the similar problem to this back in section 7.2, I had you notice that on definite integrals of this type, it is better to evaluate the integral as you go. So even though the formula is for an indefinite integral, we have to put bounds on this, and we have to put bounds on this. So n equals 6, plug everything in, whole bunch of stuff happens, right? So negative 1/6 cosine x sine to the 5th x. Now we need to evaluate that from 0 to pi, plus 5/6 integral of sine to the n minus 2. So that's integral from 0 to pi, sine to the 4th x dx. So we're going to do this formula again with this little bit here in the next step. So what I want you to notice is when you plug in pi and 0 here, right? So it's going to be negative 1/6 cosine pi sine to the 5th pi minus negative 1/6 cosine 0 sine 0. When you plug in pi, this term becomes 0. So it doesn't matter what everything else is. When you plug in 0, this term becomes 0. So it doesn't matter what everything else is. So this whole thing turns into 0. And now we did the formula again here. Right? So it's, now we're doing with n equals 4. So it's negative 1/4 cosine x sine cubed x plus 3/4, right? 4 minus 1 over 4. Integral 0 to pi sine squared x dx. And this is going to get a formula too. We can't use this formula again, because there is no sine to the 0 power. It's not defined. So we can't use this again. So we evaluate this, and you see that we have the same thing that happened before. Plug in pi, you get 0. Plug in 0, you get 0. So this whole thing becomes 0, and we're going to have to come up with a new formula for that. So it actually is formula 63 on your sheet, or if you have it up on your screen. You just plug it in. Everything else becomes 0. Now the 5/6 is still out there from before. So it's actually 1/2 x minus 1/4 sine of 2x. And you evaluate that. So it's 1/2 pi minus 1/4 sine of 2 pi. Sine of 2 pi is 0, so this is 0. Minus 1/4 0 times 0. So this whole thing becomes 0. So we're just left with 5/6 times 3/4 times 1/2 pi and get 5/16 pi. And that's the answer. And everybody's happy. So all the problems in this section look more or less like one of the two that I did. Once you know the formula, you just have to fiddle around with it, get it to do what you want, and then plug the numbers in and simplify. If it's a power reduction formula, just look up the formula. You might have to do the reduction formula a couple times. Once you get down to a sine squared or a cosine squared or a tangent squared, whatever it happens to be, use techniques that we saw earlier in the class back in section 7.2. So those formulas only work if you don't get a sine or a cosine to the 0 power in the formula, because you're not allowed to use the formula if that happens. All right, so let's talk about technology a little bit. So there's many computer algebra systems, including MATLAB, Mathematica, so that's what wolframalpha.com uses. Even graphing calculators that will solve complicated integrals. Because so many of the integrals in Chapter 7 can be solved in multiple ways, a CAS may give a different but equivalent answer than a by-hand solution. The next example shows how this can happen. So this is something you have to be aware of. If you're trying to look stuff up with a computer algebra system, you have to know if it's the same answer. So let's see what happens. So we're going to do problem 1 again, but this time we're going to use a CAS. So if you have Mathematica or your graphing calculator will do it, you can do it on there, but I'm going to use Wolfram Alpha, and I think you should too. So just go to wolframalpha.com, click on Math Input. So just do it now if you can. You can do it on your phone. It doesn't matter. You can do it on another computer. And we're just going to input everything with this math input. And what you do is you just type it in exactly the way it looks in the problem. It has all the symbols, and you can click on these things over here to change the symbols and stuff, however you want it to look. But the default symbols is plenty for an integral. Then you just click on the equals button over here. And then if you scroll down a little bit, you'll see your answer. And the answer that Wolfram Alpha gives us looks sort of like what we got in example 1. Like this part is the same. The constant is the same, but this looks different. So we need to find out if this part here is the same as the other part that we got when we did it by hand. So there's a formula from section 6.7. There's an algebraic way to write hyperbolic arcsine. And you write it in terms of natural logs. So this is what it looks like Wolfram Alpha is giving us, and this is what we got when we did it by hand. Let's prove that they're the same. All right, so let's take what Wolfram Alpha gave us and plug it into the formula. Right, there's a 4 out front, so it stays out front. This whole 4/3 x goes in everywhere I see a u. Then I'm going to simplify. All I did was I squared this whole quantity. It still doesn't look like what we had when we did example 1. So what I'm going to do is I'm going to factor out a 1/3. When you factor out a 1/3, I mean, inside the radical, you factor out a 1/9. When it leaves the radical, it becomes a 1/3. Now I got 9 plus 16x squared. Okay, so this looks like what I want. This is really close to what we got when we did the problem originally. Here's the trick. The trick is you have to factor out that 1/3 out, this 1/3 out of both of these terms to the front. Now this part here is exactly what we got when we did the problem in example 1. How do I get rid of a 1/3? So we have 4 times natural log of a third of our normal answer. So we use properties of logs, turn it into an addition problem. So this is the same answer we got, except it's this much bigger. Well, ln of 1/3 is negative, so it's this much smaller, right? So let's see what that means. So on the next slide, we simplify that integral from Wolfram alpha as much as we can. And it ended up that natural log of 1/3 to the 4th power ended up being negative natural log of 81. The integral we got by hand is almost exactly the same. Here we have negative natural log 81 plus k. I just gave it a name that wasn't c, because we were going to use c for this one. Well, this is a constant, and if I add these two constants together, I can get that constant. And we learned in Calc 1 that when you take an antiderivative, that there's an infinite number of antiderivatives for every function, and they differ by a constant. That means these two answers are indeed the same, even though they didn't look the same at first when we first saw them. It turns out that they are considered to be equivalent as integrals because they're only different by a constant. So this is algebra that you need to be able to do, because you need to be able to verify that something you get on a calculator is in fact the right answer, and it's something that you would get by hand, just to make sure that you're doing the problems correctly. Because as you've probably figured out, some of these problems are pretty tough. You might want to use some technology just to check your answer. Can't do it on test, but I mean, for the homework or for studying, it's definitely a good habit to get into, to always check your answers using technology. In fact, that's something I encourage since Chapter 5, as you recall. All right, well, that's it. If you have any questions, let me know. This is a pretty wide open section. Feel free to try different things and just, it's similar to section 7.5 in that way. But most of the stuff is really straightforward. Find the right formula, match up the form, write down u equals this or a equals this. Make sure you compute du and move stuff around if you need to. And you should be good to go. So I'll see you next video. Bye-bye now.